idea of fossil correlation. And so what we know from biology is that we know the order that different species have evolved in. And we can use that to help us date rock layers. And so what we've got for you is a puzzle to solve. And so the first fossil, Eutepterid, has been done for us. And so you can see that that would be this little like lobster-looking critter here. But what we see for the clues first appears between brachiopod A and brachiopod B. So if we flip back here to our puzzle sheet, what we see is there is brachiopod A and brachiopod B, and there's that first appears Eutepterid. If we go back to our clue, it says it's still found in layers younger than the layer of brachiopod C. So younger than means by law of superposition above. So still is going to go all the way up to that layer above brachiopod C. Now the thing about the still, we have to think about, could a fossil disappear and then reappear? No, because what that would imply is that it went extinct somewhere in this time frame but then reappeared here. That doesn't make any sense. So it can't reappear, so if we know it's found in layers younger than a certain event that's given, then we know that it would also continue all the way through. I'll do a couple more and then leave the rest for you guys. So then Bryozoan A, I cannot draw, so I'm going to use the abbreviation BA. BA is found only with brachiopod C. So I go back here to my puzzle board, and I'm just going to write a BA right in there because it's found only with brachiopod C. So that one's done. And then you can, I'm just going to write the abbreviation so I know I've done it. Bryozoan B, I'll use the abbreviation BB, first appears with brachiopod B. So brachiopod B is right here. First appears means it can't go lower than that because that would imply that it was younger than, and that doesn't work. Still found in layers younger than brachiopod C. So that means my BB is going to go up here and continue upwards to there. I'll do a couple more. Crinoid A is found only with brachiopod B. There's brachiopod B, so I'm going to add a crinoid A in here. And one more. Crinoid B first appears between brachiopod B and brachiopod C. Brachiopod B, brachiopod C. So my crinoid B, I'm going to abbreviate CB. It's going to start here. Also found with Bryozoan A. Well, Bryozoan A, it's up here. So I'm going to add a CB up here. Bryozoan B. Bryozoan B's are already here and here, so I'm not going to do anything. I'm not going to add or change anything there. But it's also found with mollusk D. I don't have any mollusk D's yet, so I'm just going to let that one sit. And brachiopod C. Well, brachiopod C, I knew that because of the Bryozoan A, so I'm going to leave that alone. Not found in layers younger than brachiopod C. So I know it has to stop there, so crinoid B must be done. I'm going to come back to this clue later. When I get later on, you'll find that there are mollusk clues, and so you can find those mollusk clues in here as well. But we're going to stop there and go to the notes. So we're using this idea of index fossils to help us. To help us solve this problem. And the law of superposition, we already know that the younger layers are on top and older layers are on bottom. And so, but what we're also using are index fossils. Index fossils are organisms that live during a relatively short time frame in geologic history, and they can be used to determine relative ages of rock. So we're still going older or younger, because if rock layers in different areas have the same fossils, then the layers are the same relative age. So in what we see is in this example here, okay, what we see in this example here, oh, my autofocus isn't working so good. There you go, getting a little bit better. Okay, what we see here is we've got this like little butterfly guy right here that is the same as this butterfly guy over here. And we see this kind of snaily looking dude is the same as this snaily looking dude over here. And then this party horn dude is the same as this party horn dude here. So we know that these two layers are about the same age, these two layers are about the same age, and these two layers are about the same age. So those layers we can relatively date because they have the same index fossils. Now you'll notice that this one has like a dashed line in the background, so that's maybe like a sandstone or a shale or something. And then this one has kind of bricks. Maybe that's in some type of metamorphic rock. It's tied to the time of formation, not to the kinds of rocks, which allows it to be used even if something isn't in the same exact kind of rock as something else in another location. Okay, so this means that index fossils, these fossils that we're using here, are usually widespread. They have to be found over large areas. If it's found over too narrow of an area, it won't help us to date that rock because we won't be able to find it in separate locations. So it needs to be widespread. It's found in all types of rock. That means they're not tied to any type or kind of rock, but rather the time of formation. And that's just because rocks can have these narrow bands, like they can only be, sedimentary rock can only be formed where there's water, and so if there's no water present, you can't have a sedimentary rock. So if that one kind of fossil is only found in sedimentary rock, it's not useful in places where I might only have igneous rock. So fossils that are good index fossils will be found in all types of rock. And the last piece is they have to live for only a short period of time. That means that they develop and go extinct, one of the few times extinction is a good thing for us, very quickly. Because this increases our accuracy and our precision. And so if you think, well, I'm going to give you a non-example for this one, the horseshoe crab. So the horseshoe crab was alive when T-Rex was alive, and it's alive today. It's actually a very important organism for humans because it provides lots of, we can get medicines to prevent some kinds of diabetes for that from horseshoe crabs. Okay, so horseshoe crabs, if we found a fossil of a horseshoe crab, well, was that rock formed, when T-Rex was alive, or was it formed like 2 months ago? We can't measure very well using a horseshoe crab. It would be like trying to measure the width of your hair with a kilometer stick. It just doesn't work. It's too big of a ruler for how tiny you're trying to get. And so if it develops and it goes extinct very quickly, then we can actually make some accurate measurements. So that's the final characteristic of a good index fossil, is that it develops and goes extinct quickly. So again, they're widespread over large areas, they're found in all kinds of rocks, and they develop and go extinct quickly. So using those, we can start to look at how we can relatively date rocks even if they're not touching. Because those other examples that we've been doing so far, the features are touching, or they're touching something nearby, and so those don't work as well if they're not touching, so fossils can help us bridge that gap. All right.